Hey everybody, it's Tuesday, December 22nd, and as you can see here in the aim today, our goal for today's video is to review the key concepts involved in circular motion. And we're going to do that basically by reviewing the two sheets that were posted as your classwork for yesterday. So the first sheet we're going to start with is the conceptual sheet with the questions from the Tipper's book. And the first question I want to look at is the first question on that sheet. This was B3 SCT 100. In this problem, there was a ball being whirled in a vertical circle, and we were asked to consider the forces acting on the ball. And so the description here said a ball with a weight of 2 newtons is attached to the end of a cord of length 2 meters. The ball is whirled in a vertical circle counterclockwise. The tension in the cord at the top of the circle is 7 newtons, and at the bottom it is 15 newtons. And they tell you in parentheses here that the speed of the ball is not the same at these points. And it says 3 students discuss the net force on the ball at the top. Angelica says the net force on the ball at the top position is 7 newtons, since the net force is the same as the tension. Bo says the net force on the ball at the top position is 9 newtons. Both the tension and the weight are acting downward, so you have to add them. And Charles says, no, you are both wrong. You need to figure out the centripetal force, mv squared over r, and include it in the net force. Now, it should be clear to everybody, based on what we've been saying so far in this unit, that the best thing to do to answer this question here would be to think about the free body diagrams. And so at the top here, you have the tension coming down toward the center of the circle here, because the tension always acts along the string. And you have the force of gravity, like it always does, acting down towards the center of the earth. Whereas at the bottom, you have the force of tension acting up along the string, again, as always, and the force of gravity acting down toward the center of the earth, as always. And so the question here is asking about the top. And so at least the first thing we should say about what's happening at the top is that Charles is definitely wrong. Because Charles says you need to figure out the centripetal force and include it in the net force. I think the key thing about this that's definitely wrong is the usage of the word include. The centripetal force is the net force. It doesn't need to be included in the net force. It is the net force. And so the basic idea here is that other forces, in this particular situation, the tension and the force of gravity, supply the centripetal force. And so notice the difference here essentially between Angelica and Bo's answers is that Angelica is saying the only force that matters is the tension, whereas Bo is saying both the weight and the tension matter. And so that means the correct person here is Bo. And so the answer, there's really not a whole lot to say, is that Bo is correct. And the reasoning is, well, according to the free body diagram, Bo is correct. At the top of the path, the tension and the weight both act down. So the net force, Fc, acting on the ball is the vector sum of the tension and the weight. That's it. You add the two forces, Fg plus Ft. Because remember, as we said, whenever you are trying to write an equation for the sum of the forces from a free body diagram for a circular motion problem, you take the forces going toward the center of the circle, and then you subtract the forces going away from the center of the circle. And so here, because both the weight and the tension are going toward the center of the circle, we just add them up. We get 2 plus 7 is 9. Take a second to pause this video here and write that down, fixing or adding to your explanation whatever you might have to make it fully correct, or just copying down the whole thing if you got this one wrong. And when you hit play, we'll move on. All right, so part B of this question said, now the students are discussing the net force on the ball at the bottom. Angelica says the net force on the ball at the bottom position is 15 newtons, since the net force is the same as the tension. Bo says the net force on the ball at the bottom position is 17 newtons, since you need to add the weight of 2 newtons to the tension of 15 newtons. And Charles says the net force on the ball at the bottom position is 13 newtons. I agree that you need to take into account both the weight and the tension, but they are in different directions, so they will subtract. And it says, with which, if any, of these students do you agree? And it's important to recognize again here that Angelica is wrong. And she's wrong because she's saying the net force is the same as the tension. And as we discussed in the previous problem, both the tension and the weight contribute to the centripetal force. So just to go back to the diagram here, the point is you take the forces going toward the center of the circle, Ft, and you subtract the forces going away from the center of the circle, Fg. And so that would be 15 newtons minus 2 newtons gives you 13 newtons, making Charles correct in this instance. And so the explanation here, for the explanation I wrote, according to the free body diagram, Charles is correct. At the bottom of the path, the tension and the weight act in opposite directions, so they must be subtracted to find the net force. Now, obviously, you can write more than that, but that's the basic idea. I think it's important to realize before we wrap this up here that makes a lot of sense if you really consider what's going on, because this ball has an inertia, which leads it to want to move in a straight line tangent to the circle in the direction of its velocity vector shown here in the diagram on the right-hand side. And as it moves from the top position to the bottom position, it's being accelerated by a component of gravity, which is making it speed up. And so it's going faster on the bottom than it is at the top. And the key detail is not only does the tension have to support the weight of the ball, but it also has to deal with the fact that the ball is trying to move essentially away from the direction the tension is pulling. And since essentially the velocity here is like tugging against the tension, the rope has got to pull even more to be able to hold the ball into the center of the circle. And that's why the tension here is 15 newtons. Take a second to pause this video here and write that down, adding to your explanation whatever you may have that is missing, or just writing it down completely if you got this one wrong. And when you hit play, we'll move on to the next question. Moving on to the back part of the sheet. First question on the back part of the sheet was B3CT 101. Skateboarder on a circular bump, weight and normal force. It says a skateboarder is skating over a circular bump. At the instant shown, she is at the top of the bump and is moving with a speed of 5 meters per second. Is the normal force exerted on the skateboarder by the bump greater than, less than, or equal to the weight of the skateboarder? Explain your reasoning. Once again here, the basic answer to the question is determined by the free body diagram. And so we have the normal force going up, and we're going to have the weight coming down. And the weight here has to be bigger than the normal force. Why? Because the net force has to be toward the center of the circle. And if the net force is toward the center of the circle, the only force that's acting toward the center of the circle is Fg. So the normal force has to be smaller than the weight. The weight has to be bigger than the normal force, because when you take Fg minus Fn, we need to get a number that's greater than 0. And so the answer here, the explanation is pretty simple. The skateboarder is moving in a circular path, so there must be a net force acting toward the center of the circle, down. As a result, the downward force, Fg, must be larger than the upward force, Fn, in order to produce a net force toward the center of the circle. That's it. It is that simple. Take a second to pause this video here and write this down, adding to your explanation whatever may be missing, or just writing down the whole thing completely if you got this one wrong. And when you hit play, we'll move on to the next one. All right, moving on to the last one on this sheet here, B3 SCT 102, child on a swing, tension. This is one of these questions again where we have 3 competing explanations. It says a child is swinging back and forth on a tire swing that is attached to a tree branch by a single rope. Shown are 2 positions during a swing from right to left. 3 students are discussing the tension in the rope at the bottom of the swing. Alia says at the bottom of the swing she will be moving exactly horizontally. Since she is not moving vertically at that instant, the vertical forces cancel. The tension in the rope at that instant equals the weight. Brian says, just looking at the velocity vectors, the change in velocity points between A and B. So that is the direction of the acceleration and also of the net force. To get a net force pointing upward, the tension would have to be greater than the weight. Clara says, but there aren't just two forces acting on her at the bottom of the swing since she's moving in a circle. There's also the centripetal force, which acts towards the center of the circle. Since both the tension and the centripetal force point upward and the weight points downward, to get zero net force, the tension actually has to be less than the weight. The tension plus the centripetal force equals the weight. And it says here, with which, if any of these students, do you agree? Alia and Clara have two fatal misconceptions in their answers. And that makes them wrong. And that means Brian is correct. And so as we can say here, when the swinger moves along the circular path, there is an acceleration up toward the center of the circular path. As a result, the upward force must be larger than the downward force. And I'm just going to write here, so F net is up. Sorry, it's very hard to write on this image for some reason. The basic idea here is that Alia says at the bottom of the swing, she's moving exactly horizontally. True, I guess, but it doesn't matter. Because she's still moving in a circular path, there must be a net force toward the center of the circle here, which happens to be upward. And notice, Clara says another extremely fatally flawed thing, because what she says is that, you know, we're accounting for the tension and we're accounting for the weight, but we're not accounting for the centripetal force. And it's very important for everybody to realize the centripetal force is not a separate force, but rather, as this should say, rather, it is the vector sum. It is the vector sum of the tension and the weight, where, of course, the tension acts up and the weight acts down, so they have to subtract. And the basic detail is if Ft minus Fg is a greater than 0 number, the Ft has to be bigger than the weight. Notice the misconceptions that this sheet is driving at. A lot of people, for circular motion problems, get confused about the requirement that the net force has to be pointing toward the center of the circle, that means whichever force is pointing towards the center of the circle must be bigger than the force pointing away from the center of the circle, and that the centripetal force is not a separate force, but rather is the sum of the individual forces acting in the problem. The centripetal force is not a new force. It is simply the name we give to the net force when that net force happens to be acting towards the center of the circle and causing an object to experience circular motion. That's the basic detail. Take a second to pause this video here and write that down. And when you hit play, we'll move on to the next sheet. Moving on to the next sheet here. On this sheet here, now we have problems for you to solve, free body diagrams for you to draw, equations for you to derive, etc., etc. It says here in this one, and we'll do the first one on the front and then the back one, a block is sliding along a frictionless surface as shown in the diagram below. At the instant depicted in the diagram, the object is located at the very bottom of the hill. And the first part here says to draw the free body diagram for the block when it is located at the bottom of the hill. And the question says to ensure your diagram reflects the relative magnitudes of the forces acting on the block. And so as we've been saying this whole time, when, you know, from when we started talking about regular forces, not even circular motion problems, the first thing that we should do when we're drawing a free body diagram is ask ourselves the question, which objects is the object in question, in this case the block, which objects is the block interacting with? And the answer is pretty simple. The block is interacting with the Earth, and so we are definitely going to have a force of gravity in our diagram, and the object is interacting with the surface of the ramp, and so we are definitely going to have a normal force shown in this diagram. And the extra question you need to consider when we're doing circular motion problems is really quite straightforward. The question you need to ask yourself is, which one of these forces is pointing toward the center of the circle? And the answer here is the normal force. And so your diagram should look like this. And as I wrote here as a side note, which obviously you don't have to do in these problems, but as I wrote here, Fn is greater than Fg because in order for F net to point toward the circle's center, the force toward the center of the circle must be larger. And so here off to the side, if you want, remember it is totally cool if you put that AC showing the direction of the acceleration, but the basic detail is because the person is at like the valley of a ramp, the center of the circle is actually up. So that means the normal force must be bigger than the weight. Notice here, this is the exact opposite of the hill problem that we looked at on the last sheet with the skateboarder going over the hill. When the skateboarder is going over a bump, the center of the circle is down, but when the skateboarder or whatever object it is moving like in the valley of a hill, then the center of the circle is up. Take a second to pause this video here and draw this diagram correctly, or write down this note if you didn't already, because this is a very important note. It comes up again and again and again. Notice, especially on that concept sheet we just answered. And when you're finished, hit play, and we'll move on to the next part. Part B is asking you here to write an equation for the sum of the forces acting on the crate using your diagram. And so we mentioned this in the last sheet earlier in the video here, that whenever you're writing an equation for a free body diagram from a circular motion free body diagram, for one of these circular motion problems, you take FC and you set it equal to all the forces going in the direction of the center of the circle, and you subtract all the forces going opposite the center of the circle. That means your equation should look like this. We have FC equals Fn toward the center of the circle minus Fg, which is opposite the center of the circle. And you didn't need to do this second line here. I just did just because I figured, we might as well. We're going to have to use it in that form later. I changed FC and subbed in mv squared over r, which is the equation for the centripetal force. And I put in the normal force minus mg for the normal force minus the weight part. And that's it. Now here, it's important to realize the equation, pretty straightforward here. It follows the rules for the regular free body diagrams as we used to discuss those as well. We take MA, which in this case happens to be AC, but still, we take MAC and we set it equal to the forces going in the direction of the acceleration, which here is centripetal acceleration, so it goes toward the center of the circle, and then we subtract the forces going in the opposite direction. Take a second to pause this video here and correct your work if you need to, and when you hit play, we'll move on to the next part. Part C says determine the force exerted on the 200 kilogram block by the track if the block is moving with the speed of 10 meters per second. And so here, this is a pretty straightforward problem-solving question now that we have the equation from the previous part. And so your work should look a little something like this. Notice here in my list of knowns, I have the mass, 200 kilograms. I've got G, 9.8 meters per second squared. I've got the speed that they told us here in this problem, 10 meters per second. And I got the R, which they told us in the very beginning. Notice that was shown in the diagram, was 25 meters. And so we have our knowns. The normal forces are unknown. And so we have mv squared over r equals Fn minus mg. And then we just rearrange it to solve for the normal force. Notice it says determine the force exerted on the block by the track. And so that means here we're looking for the normal force. So we have mv squared over r plus mg. We get that by adding mg to both sides. And notice, because I didn't feel like plugging in the mass twice, I chose to just factor it out. And so essentially I have v squared over r, which is AC, right? AC, centripetal acceleration, is v squared over r, plus the acceleration due to gravity, times the mass here, 200 kilograms. And when you do that math, you get 2760 newtons, which for no reason other than, well, they gave me 25 meters to 2 sig figs, I decided to just call it 2800 newtons. Again, rounding, not really a huge deal, but that's the point. Take a second to pause this video here and write this down. Correct your work if you need to. And when you hit play, we'll move on to the next problem. All right, moving on to the last problem, we have the conical pendulum problem. This one is a little brutal, but hopefully after the examples we looked at the other day, this one will seem a little more straightforward. It says here a 0.456 kilogram ball tethered to a small pole on a 1.25 meter long rope is thrown so that it travels in a horizontal circle with a rope making an angle of 35 degrees with a vertically oriented pole. Draw a free body diagram of the ball. And so it should look like this. It's not really that hard. We talked about this a lot just recently. So all we really have to say is, again, when you're drawing a free body diagram, you ask yourself the basic questions. Which objects is this object in question interacting with? In this case, it's a ball. So which object is the ball interacting with? And the ball's interacting with the string or the rope, and the ball is interacting with the earth. So we have a force of tension. And it doesn't really matter which way you drew this, just as long as it was at an angle. Usually in these problems, they give you a picture, but I couldn't really fit it on the page. And so if you imagined the ball being tethered like this, then your tension would look like that. If you didn't imagine that and you imagine the ball being tethered like this, then your picture would sort of look like that. Again, not really that big of a deal. It doesn't really matter. But the main idea is you should have the tension acting at an angle, and you should have the force of gravity coming straight down. Take a second to pause this video here and sketch that in case you missed it. And when you hit play, we'll move on to the next part. All right, moving on to the next part here. The question said, what is the physical significance of the X and Y components of the tension? And we talked quite a bit about this fairly recently as well. The physical significance of the X component of the tension is that it supplies the centripetal force. It is the only force acting toward or away from the center of the circle, and so it supplies the centripetal force. The Y component of the tension, on the other hand, supports the ball's weight. And that's the idea here. Pretty straightforward. The Y component is the only other force acting in the vertical direction besides the weight, and the object is not accelerating vertically. So those got to cancel. And then in the X direction, well, the X component of the tension is the only force acting, and it happens to be pointing towards the center of the circle, and so it's supplying the centripetal force. That's the point here. Take a second to pause this video here and write that down in case you missed that, although I would imagine you didn't. And when you hit play, we'll move on to the next part. The next two parts here, D and E, ask you to write the equation for the sum of the forces in the X direction. And so the idea here is pretty simple, I think, D and E. It says we got to write the sum of the forces. And really, all you need to do is just utilize the concepts that we just discussed. For the X direction, the centripetal force is being provided by the X component of the tension. So we take the equation for the centripetal force, mv squared over r, and we set it equal to the equation for the X component of the tension, which is ft sine theta. Very, very important for these problems to remember the sine and the cosine switch for a conical pendulum. Remember, the inclined plane and the conical pendulum are the only problems for which this applies. Instead of sine going with y and cosine going with x, they switch. For the y direction, again, we utilize that concept we just discussed here, that the weight is being canceled out by the vertical component of the tension to prevent vertical acceleration. And so we just take the equation for the weight, mg, and we set it equal to the equation for the vertical component of the tension, fty, which is ft cosine theta. Take a second to pause this video here and write that down if you need to fix anything in your work. And when you hit play, we'll move on to the next part. All right, moving on to the next part here. F says to determine the speed of the ball. And for this question, you basically just needed to solve your equations from your free body diagram as a system of equations. And so notice the first thing I did here, I'm going to sort of go through this step by step. The first thing you needed to do here was you needed to write down your list of knowns. So I have the length of the rope is 1.25 meters. I got the mass of the object is 0.456 kilograms. I got my angle, it's 35 degrees. G is 9.8 meters per second squared. And V is our unknown. The important thing to recognize in these problems when they give you the length of the rope is that eventually you're going to need the radius of the circular path in which this thing is moving. And you can find the radius of the circular path in which this thing is moving by using the fact that a cross-section of the cone that is made by this conical pendulum, again, that's the reason why it's called conical, because it forms a cone, that the cross-section of the cone is a right triangle. And so Essentially, the relationship here is that this is the opposite side from the angle. Remember, we use vertical angles in these problems. That's why the sine and the cosine switch. The radius is the opposite side. The length is the hypotenuse. And so we have r equals L sine theta. So your first move for these problems should be to take the y direction equation first. It's the simpler one. And you solve it for the tension. All you really have to do here is divide both sides by the cosine of the angle. So we have mg over cosine theta is equal to the tension. Then I did the same thing for the x direction. I wrote out the full equation, mv squared over r equals ft sine theta, and then I just solved it for the tension, this time dividing both sides by the sine of the angle. That gave me mv squared over r sine theta. Now, the key here to solve for the speed is that you don't know the tension. And so the easiest way to solve for the tension is to just set the two ft terms equal to one another. And so we get ft equals ft, and that gives you mg over cosine theta equals mv squared over r sine theta. Now, the key insight, although it doesn't really matter because you knew the mass, but a key insight here is that the masses cancel. That makes sense because a heavier object would require more of a centripetal force, meaning more of an x component of the tension. But the very fact that the object would have more mass automatically means the tension would be bigger because the y component of the tension would have to be bigger. And so it just works out like that where we get this cancellation effect. And so essentially what you need to do is just manipulate the variables to go ahead and solve this thing for v. And so the first thing you do is you take the equation and you solve it for v squared. You do that by moving the r sine theta up and over. So we get g times r sine theta over cosine theta. And that gives you gr tan theta. Because notice sine over cosine is tangent. That comes up again and again and again. So now that I have gr tan theta, I can sub for r the equation that we have for r from the cross section of the cone, which is L sine theta. That gives me that v squared is equal to g L sine theta times tan theta. There very well may be a trig identity that I am not aware of that has you rewrite the product of the sine and the tangent as something else. Like you've probably seen before by this time in your education, like double angle formulas or various trig identities. It doesn't really matter for this, though, because you have the angle, so doing sine theta times tan theta is perfectly easy. And so that's what you do. You have square root of GL sine theta tan theta, and all you have to do is plug it in. So we have 9.8 meters per second squared times 1.25 meters times the sine of 35 times the tangent of 35, and then all under square root. And when you do that math and you plug it in, you get 2.22 meters per second. Take a second to pause this video here and write that down, fixing any part of your solution that may be missing, correcting any mistakes you made. And when you hit play, we'll move on to the final part. Okay, moving on to the last part of this sheet here. G says to determine the tension in the rope. And before I show the solution, I just want to go back and recognize that you actually could do that using the equations you have now that you know the speed. Either equation can be used. I'm almost always for these parts going to use the equation mg cosine theta just because I find it to be easier. I don't have to square anything. There's only one variable in the denominator. I don't want to go nuts about it. But of course, you need the mass for both. And the only other thing you need for the y direction equation is the angle. If you have that, you're in business. You actually could have used that to solve for it first. It's also important to realize if you just found the speed, which we did, then you could use the x direction equation as well here, because even though we don't have r, we do have an equation for r that it's L sine theta, and so you would have mv squared over L sine squared theta. Either way, your work for the tension could look like this. It should give you that answer. Here I have the mass is 0.456 kilograms. G, of course, is 9.8 meters per second squared. The angle theta is 35 degrees. And the tension here is our unknown. And so the equation mg over cosine theta gives us an answer. We have 0.456 kilograms times 9.8 meters per second squared times the cosine of the angle, 35 degrees. And that gives us a tension of 5.46 newtons. Take a second to pause this video and write this down, fixing any part of your calculation that may be missing or any mistakes you might have. And very quickly before we go, I just want to take a quick look at some of the multiple choice questions in the personal progress check for forces that large numbers of you answered incorrectly. When you hit play, we'll get into that. All right, quickly before we go here, I just want to take a look at a couple of the questions in the personal progress check that was assigned for homework over the weekend. Overall, the results were great. Everybody was in the green. Almost everybody was in the dark green, which is very good. Having said that, there were a few questions which large numbers of people got wrong, and so I want to make sure that we go over those. So the first one is question number 1. Question number 1, and I think the order was different for all of you, but it says inertial mass of a cart here as the title. And this question says, a student sets up an experiment to determine the inertial mass of a cart. The student has access to the following measurement equipment: a spring scale, a meter stick, and a stopwatch. The student uses the spring scale to pull the cart starting from rest along a horizontal surface such that the reading on the spring scale is always constant. All frictional forces are negligible. In addition to the spring scale reading, which two of the following quantities could the student measure with the available equipment and then use to determine the inertial mass of the cart? Select 2 answers. A key thing that everybody should realize here is that the inertial mass of an object is the mass in the equation F net equals ma. It's the mass in Newton's second law. And so if you are being asked to determine the mass of an object from Newton's second law, the idea here is pretty straightforward. If F net equals ma, then m is equal to F net over a. Since you already have F net, and if you didn't realize it, you do already have F net because they tell you you are being given the spring scale reading, then what you needed to measure was the acceleration. And so almost everybody who got this one wrong in some part picked the average speed of the cart while in motion, and that doesn't give you what you need. Because in order to find the acceleration, especially when it says here that the cart is starting from rest, the best equation to use would be the equation delta x equals v naught t plus 1/2 at squared. If you use the equation delta x equals v naught t plus 1/2 at squared, then if the initial velocity is 0, to solve for the acceleration, you just get 2 delta x over t squared. And that means if you measured the displacement and you measure the time, you can use this equation to solve for the acceleration, which then you can use to find the inertial mass of the cart. That makes the answers here A and D, the distance and the time. The reason why the average speed of the cart while in motion is wrong is because a meter stick, a stopwatch, and a spring scale cannot be used to directly measure the average speed of the cart. The average speed would need to be calculated from the measurements of the distance traveled and the time to travel that distance. I actually think that's a stupid explanation. I kind of wish I hadn't read it to you. But the point is, even if you use the distance and the time to calculate the average speed, so it's not technically measured, which is true, more importantly, the average speed doesn't give you the acceleration in a straightforward way, especially unless you get the time. And so it's very important. Now, notice the same reason why C is wrong is because it does say measure with the available equipment, and you can't measure the acceleration directly with the equipment either. So despite the fact that I think that reasoning is a little silly, they are looking for that on the AP test. And so that's an important thing to keep in mind. All right, moving on here. As you can see, the next one a bunch of people got wrong, these ones were all good, is number 6, fan-powered toy car. And so in this question, you're going to have a fan-powered toy car that has a battery-powered fan attached to it such that the fan creates a constant force that is exerted on the car so that it is propelled in the opposite direction in which the fan blows air. Right? That makes sense. The fan pushes on the air backward, and so the air pushes on the fan forward. and that's why it moves forward. It says the car has a carriage that allows a student to attach objects of different masses as shown above. The fan only has one speed setting. All frictional forces are considered to be negligible. Which of the following procedures could be used to determine how the mass of the fan car object system affects the acceleration of the system? That's another experimental design question. You got to make sure you're writing down the equations for these. It says here the correct answer is A. Measure the mass of the system using a balance, activate the fan, measure the distance traveled by the system at a known time using a stopwatch, and repeat the experiment for several trials with different objects added to the carriage. It's very important to realize they love asking questions where you have to use this equation to calculate the acceleration. 2 delta x over t squared is a really clutch equation to use for experiments because measuring acceleration is annoying unless you have technology. But if you just say, forget it, the object is going to start from rest, I'm just going to lay down a meter stick and a stopwatch and use that to measure the distance and the time, you can calculate the acceleration using this equation. 6 people picked choice B, which says measure the mass of the system using a balance, activate the fan, use a meter stick and a stopwatch to measure the initial and final speeds of the system, and repeat the experiment for several trials with different objects added to the carriage. The issue here is in measuring the initial and the final speeds. It's just going to be complicated. It says, while there is a way of determining the acceleration of the system using kinematic equations that contain information about the initial and final speed of an object, a meter stick cannot be used directly to measure initial final speed. So notice they keep going back to this about what can be directly measured. And so the idea is if you're using the stopwatch to measure the initial speed by having it travel a certain distance, and using it to travel a certain distance for the final speed, you're not measuring the amount of time it takes for it to transition from one speed to another, and that's what's needed to calculate the acceleration. And notice it's going to be the same thing. Well, actually, it's not the same thing for C, because for C, it says measure the mass of a system using the balance, connect a spring scale to the back of the car, and measure the amount of force required to hold the system at rest. The question is not saying anything about it being at rest. It's saying, how does mass affect acceleration? If you're not allowing it to accelerate, then you can't possibly use that experiment to determine the relationship between the mass and the acceleration. So a crucial detail for these problems is going to be writing down the equations and seeing what equipment they're giving you and how that equipment can be used to make whatever measurements are required. Next question is number 7. Actually, more people got this wrong than right. It says students connect a spring scale to a block on a rough horizontal surface. The students use a spring scale to measure the magnitude of the horizontal force needed to pull the block at a constant speed. Which of the following statements explains why 2 forces exerted between the object are equal in magnitude? Most people picked B, the frictional force and force exerted by the spring scale on the block, because they are a Newton's third law pair. That is wrong. It's very important for everybody to realize, and it's the same thing for A, action-reaction pairs can only include the same 2 objects. A is wrong because the gravitational force is a force exerted by the Earth on the block, Earth on block. That means the reaction is block on Earth. Earth on block, block on Earth. That doesn't involve the surface, so it doesn't involve the normal force. The normal force is a force exerted by the table on the block, and so that means the reaction is block on table. Table on block, block on table. Same thing with B. B says the frictional force and the force exerted by the spring scale on the block. The frictional force is a force exerted by the table on the block. Block on table, table on block. That's the pair. For the force exerted by the spring scale, it's scale on block, block on scale. They can only involve the same 2 objects. The answer is D because it says the frictional forces that the block and the surface exert on each other, because objects always exert forces of equal magnitude on each other. The table exerts a force on the block, and the block exerts a force on the table. Those are the same 2 objects, and so Newton's third law applies. It says correct reasoning statement, the block and the surface exert a frictional force on each other, and these forces are a Newton's third law pair. That's the idea. They always exert forces on each other that are equal and opposite if it's the same 2 objects in question. Okay, moving on. 13. A lot more people got this wrong than right. And so it says here we got a block and acceleration graph. And so it says here, Block A is placed on a rough surface inclined at an angle theta above the horizontal. A taut string connects block A over a pulley to block B, which hangs from a string as shown below. The masses of blocks A and B are MA and MB respectively. At time t0, block A is sliding up the slope as block B falls, and both blocks are slowing down. Assume that mass and friction of the pulley are negligible. The two blocks eventually stop in reverse direction. Which of the following graphs best predicts the acceleration of block A as it moves up and down the rough inclined surface? Assume that positive direction points down the slope. And so the answer here, as is shown by all these graphs, is B. The block is slowing down in the beginning. That's what it says. And so if it's moving up the ramp and positive is down the ramp, the acceleration's got to be positive the whole time. So that rules out C and D, which 14 of you picked. If it's moving down the ramp and speeding up, or moving up the ramp and slowing down, the acceleration has got to be down the ramp. So the question here is, well, why isn't the net force, and thus the acceleration, constant the whole time? And the idea here, I think, is pretty straightforward. In the beginning, you have to think about the free body diagram. In the beginning, you got this block moving up a ramp. And when the block is moving up the ramp, you have the tension acting up, and you have FGX acting down the ramp, and you have the force of friction acting down the ramp. On the way down, it's just the force is combining in a different way. The tension still acts up the ramp, but now so does the friction force, where only FGX is acting down. And since only FGX now is acting in the direction of the acceleration instead of the two forces from before, the force in the direction of the acceleration, and thus the net force, has to be smaller here. And because it has to be smaller here, it makes the acceleration smaller. And so as it says here, the acceleration of block A is only down the slope, but the direction of the frictional force changes when the block changes direction and begins to oppose the component of gravity down the slope. They ask a lot of questions like this on the AP test, things moving up or down ramps and reversing direction on the ramps and asking you to compare various quantities. The key detail is that when an object is on a ramp, depending on which way it's moving, means you have different combinations of the forces because certain forces can change direction. FGX is always going to act down the ramp. If there's a string, the tension is always going to act up the ramp. But the friction force always acts opposite the direction of the motion. And that's the key detail behind that one. And we'll just review 18 and 19. 18 says, which trial is there a greater electromagnetic force? Now, we haven't talked about electromagnetic force really at all yet, but most of you got this one right. It says a student uses an electronic force sensor to study how much force the student's finger can apply to a specific location. The student uses one finger to apply a force on the sensor, and data collected from the two trials is shown in the table. During which trial, if any, does the student's finger experience the greatest electromagnetic force? 7 of you picked an electromagnetic force is not exerted on the student's finger in any trial because the only force that the sensor applies to the student's finger is a normal force. Well, first of all, for the one person who picked the sensor does not apply any force to the student's finger, of course it does. It's an action-reaction pair. Finger on sensor, sensor on finger. For everybody who picked D, the normal force is an electromagnetic force. It's an important thing to remember. The reason why normal forces exist is because the valence electrons in both of the objects at their surfaces, that's why we always talk about surfaces for normal force, because the valence electrons are at the surface. It's a repulsion of the valence electrons. And so here, it says correct. Trial 2 is the trial in which the student exerted the greatest force on the sensor. Based on Newton's third law, the force that the student applies to the sensor will result in the sensor exerting a force on the finger, while the force that the sensor applies to the student's finger is typically classified as a normal force. The normal force arises from the electromagnetic interactions of the atoms and the molecules at atomic levels that typically experience a repulsive force. That's the idea. You got repulsion of valence electrons. The normal force is an electromagnetic force. And the last one here, question 19, force diagrams during collision. At time t equals 0, object x on the left here of mass m travels at a constant speed of 2 meters per second to the right toward object y of mass 2m. That is a distance 8 meters away from the object while at rest, as shown above. Both objects are on a horizontal surface where frictional forces may be considered negligible. Which of the following pairs of force diagrams represents the forces exerted on the objects x and y at t equals 4 seconds? The first thing you should be realizing is that if this is 8 meters away and this block is going 2 meters per second, it's going to hit at 4 seconds. So they're asking which diagram shows you the forces when they hit. Everybody who picked choice A got this one wrong because you did not show any contact forces between objects x and y, and they're in contact. They crashed into each other by 4 seconds. That's why A is wrong. Let's just go on to the other ones. C and D are both wrong for the exact same reason, because those diagrams violate Newton's third law. The force that x exerts on y has to be the exact same as the force from y on x. Notice in C and D, these arrows are different lengths, showing the forces are different sizes, and that cannot possibly be true. The answer here is B, because first of all, y is heavier than x, and so the normal force and the gravitational force on x is smaller than the normal force and the gravitational force on y, and also it shows that the mutual forces these objects exert on each other when they collide are equal and opposite. And that's it for the AP Classroom assignment and this video. Have a good one, everybody.